Okay, now I want to talk about some basic scenario, but at the same time I will look at this scenario from another angle. And namely, I want to describe how Git handles our scenarios of creating files and committing the changes to the repository, and how it stores all the information that is necessary to keep track of all the previous states of our repository. So I'm creating an empty repository here, and let's start from the simplest operation we can do. Let's create a file first and add some content to it. And so now what we're gonna do, we want to add this file, right? And if you remember, a commit like git commit -a to add all the files won't work here, because you don't have anything in stage area to be committed, and you add files, and this is so because this file isn't yet tracked by our repository. And what do I mean by that? There is this feature called index, or stage area of our repository, that basically shows the latest version that repository is known of. And you can inspect this index, this stage area, by command git ls file, and you provide a stage flag just to view everything that is ready to be committed, the latest version of our repository that's not yet in the commit history, but we can commit it. And we don't have anything here because we don't Git doesn't know anything about this file. On the other hand, let's maybe add it a usual way and commit file1 edit, add file1, and now we have one commit, and actually now our repository knows about this file, and whenever we change it, update one to file1, and now we take a look at stage area, we'll see that this file is actually in the stage area, and this means that git commit -a all will be able to find this file, and because -all will try to add every file from working directory to stage area before it creates a commit, and it will try to add every file that it knows of. It knows of this file, so it will try to add it. And what this is basically the identifier of the object that shows what was the state of this file during the latest version of this file known by repository. So if you want to actually inspect what was in this file during the latest commit, you run command git cut file, and you provide a type of our object and then identifier. Okay, actually it's not commit, it's called a blob, but I will return to the name a little bit later. And here's our content. So, and now what? We have this stage area that we can inspect with files, ls files, stage, and it stores the latest version of the files presented in Git, and we now and our repository knows only about a single file right now. So let's try to create another file, and actually if we changed the content of the file and we type git diff. Git diff command will show us the difference between our head and current working directory. And as you can see, it has this line here, and basically what it shows us is a previous index, a previous identifier of the content, a previous version of a file that we can inspect, and what it will become if we add this change to stage area. Because if we add the file to a stage area, and because the content was changed, this object will be recreated. Actually not recreated, but Git will create another object with the new contents of this file, and it will store it to the local database, and then we'll use it to reference a new version of the file. So we can, I don't know, can we actually, is it actually already created? So now let's try git cat file blob. Okay, I guess it's not yet created, but if we are going to add a file to a stage area, and now if we type git diff, okay, we don't have anything because these changes that we okay, why we don't have anything? Because git diff had, okay, git diff by default showing you the difference between a stage area and a working directory. And now that we added our file to a stage area, we don't have any changes, any difference between a stage area and a working directory. If you provide a staged flag here, it will show you the difference between actually let's take a look at documentation. Okay, we need this form when we specify git diff, and commit is optional. Commit should be optional. No index. Here is it. This form is view the changes you made relative to the index staging area for the next commit. In other words, the difference are what you could tell Git to further add to the index, but you still haven't. You can stage these changes by using git add. So basically git add will show you the difference between stage area and a working directory, and git staged will show you the difference between the latest commit and a stage area, right? And git diff head, for instance, will show you the same thing. Let's take a look at the documentation one more time. This form is interesting for us now. This form is view the changes you have in your working tree relative to the named commit. You can head to compare it to the latest commit, or a branch name to compare with the tip of the directory branch. So basically what it means is that git diff head will show the difference between our latest commit and the working directory, and because we have a in our working directory the file that is kept tracked by git and changed, we see it here. And if we restore the file from stage to untracked, and if we now type git diff head, we'll see the same output, right? Because it doesn't matter did we actually add a file to a stage area or not. It's in the working directory, and Git will compare it to a head anyway. So now we don't have anything in staged area. Let's add our file to the stage area one more time. And now let's take a look at the index. As you remember, we have let's actually restore this file again and take a look at our index. And we have this file. This file has one line in it right now, and Git identifies this file by this identifier. And what it is this is a reference to a blob. A blob is a file content. So you take to view the file. Let's repeat it. Let's repeat the operation. You take identifier, and you can view it with git file blob identifier. And here's our old content. And remember that for further demonstration, remember that the first letters, the first character of this identifier is 6 to 4. And let's now add, and this is similar to what git diff shows us. Here is our identifier, and here is what Git will generate if we add this file to stage. So Git will create a new version of this file, and this identifier should be changed. So let's add this file, and let's inspect fs files stage right now. Oh, not fs but ls. And here we go. We have a new content of the file, and we have we basically have a new blob here, and we can inspect it with git files, cat files, blob, not file but file, and here we have 2 lines of our file. And how you remember this command? Well, it's basically very similar to Linux standard cat command that can show you the file like so. As you can see, it has some similarities. The only difference is that Git stores all this information in database in binary format. So you need to have some tool to actually understand what to actually decode these records in the database, and this is why you use cat file. And you can view 3 more different record types and object types, but I will mention it a little bit later. For now, let's move on and let's actually commit this file. So now we have this file in our index, right? And the content is changed. And you need to know that this contents will, this identifier will only change if you update the file. Git won't create a new blob file for every commit, for every file, if the file isn't changed. Only files that are changed, well, it will create blobs only for the files that are changed, and won't touch all files that were not changed during this commit. So, and to see it in practice, let's actually commit this file, right? Commit change file 1. right? And now if we inspect, now index should point to the latest commit because we don't have any new upcoming changes. Here's our file with the latest version, and here's a question: how can we inspect a previous state of the file? Because it somehow should be mentioned in the commit history, because each commit represents the state of our repository, and we should be able to view the contents of the file, for instance, on our initial commit. And there is a way, and there is exactly where commit objects come into play, because commits, similar to blobs, are stored in the same database, and you can view the commits in very similar fashion. You type git cat file, and instead of a blob to view a file, you type commit and provide the identifier, and this is the content of our commit. It's very similar to what we see in git log, although it has this important field, a tree, right? And a tree is a third type of the record that Git stores in the database, and tree is very similar to what Git ls files shows, because if you take a look at ls files, it basically stores all the information about the states of our repository at specific commit, and tree does exactly that. And we have, for each commit we have in our history, we have a tree. It doesn't work the same way with index. We have only a single index, and then when index is committed, it creates a tree for us to keep track of specific commits, and we can go back in history to actually view the state of specific of our repository at our commit, a specific commit. And to view a tree, there is another tool called lstree, and we provide the identifier of our tree to lstree, and we will get the list of files in the repository at the specific time, point in time in the past. And here we have our old version of file 1, and we can, and this is actually called a blob here, we can take it and inspect it with git cat file blob identifier. Here's our old one, and the same way we can go and inspect a new version of the file. And we have only a single file in the repository, but here could be a list of files, and it actually equals to what well, it's very similar to what tree command shows us in our file in our folder. It basically will store all the files and all the folders in hierarchical structure. I'll show you it a bit later. But for now, let's continue with investigating the new version of the file 1, how we can get it. Very simple. We just, well, the first thing that we have already known about is git ls files stage, and we can cut file with this identifier, or we can take this commit. Actually, not only the commit, but we can inspect commit record by providing a marker or a pointer with commands. So we can use git cat file commit not only with identifier, but also you can provide head, or for instance a parent of the head, or a master, right? let's stick with the master this time, and here is our second tree, and here we have an extra option that we didn't have previously. Let's quickly remind the initial commit. Git file commit head. The parent of head doesn't have, or the initial commit doesn't have a parent, because this is our first commit in the repository, but here we have a parent that points to our head commit, and this is head, and you can see it right here, identifier of the, this is actually this is a head commit, and as a parent it points to the initial commit, so we have identifier of the initial commit here, and it's equal to identifier in git log. So now we see the tree of the master branch, right? Which means it stores the current state of the repository, and we view this tree by the same command, git ls tree, providing the identifier, and here our file 1, and a blob is changed for it, right? And we can view the blob with git cat file blob, and here's our updated file 1. So you see now that index and a tree is kind of related to each other, because when you are preparing the commit, you create an index, right? You change an index because you always have an index, and in case of a new upcoming changes, index is changed. Git changes index by creating a new records in the database, like a blob, a new blob, or actually if you change the directory or the contents of the directory, it will create a new tree. And then when you commit a change, Git creates another tree that represents a state of the current state of the repository, and it also saves this state to the repository, to the database. And what I mean by database, well, let's take a look at how Git stores all this information, and to view that, you should find a folder called .git in your repository. And basically what it is this folder describes configurations and different references to a folder, to branches, etc. For example, let's quickly run through all the stuff that we have here, and I'll try to explain what I know. For instance, this file commit editing is just the latest message we used in the commit, right? Well, just maybe it's for simplicity to show it somewhere. The head file will show where head points to. In this case, it points to a master, and it actually a reference to another file in the folder refs. Let's inspect it next. Refs folder, heads, and here's our master, and we'll be able to see other branches here if we have more than a single one. And this file only contains the commit of our the head of our branch called master, and our master head is pointing to this commit. So it's commit, and we can indeed see that this is a commit by, for example, git show command. Here's our commit that master is pointing to right now. And before we leave this folder, here's another tags that will contain the same structure as head, only with tags. So this is about it for refs. Let's move on to config. And config stores a local configuration. To show how it works, let's configure something locally. For example, git config user name test, right? And now if we go back and view the config, here's our user. So it stores custom configuration of our custom local configurations. I will skip hooks. Well, maybe let me mention in one sentence. Hooks are small programs that runs on specific action. For example, you can create a hook to run a bash script every time you commit something. For example, this simple program will be able to check your repository for errors and maybe disable or cancel your commits in case of emergencies. So this is you just create a file for example pre-commit here, and actually it's created there, pre-commit, right? File like that, or it can store any code here, and then you change running mode to change the mode to executable, and it will run, Git will run it for you whenever some action happens. The next one is description, that basically stores the description. You might change this file, and some programs, some Git programs, Git-based programs will be able to show this content. Index is a binary file that stores a current index. It's in binary format, so we cannot actually inspect it manually. And to inspect it, we already used fs files command, and not fs but ls files. And without stage, it will only show the file name, and with stage option, actually ls files without providing any option will only show you a list of files that Git is keeping track of. In this case, we only keep track of file1.txt. And if you actually provide a stage option, it will show you all the information about the blob. This is a permission mode of our file. And yeah, let's move on to our Git folder. And info also stores some information that is not important right now, same with logs. And the latest and the most important one are objects. So if, for example, objects is basically a folder that stores that actually a database, a file system database of all these objects that we just used. For example, let's take a look at this object, and it uses this hierarchical structure. It basically takes two syllables from the object's identifier and creates a folder. Why it does it? Well, to actually speed up the process of searching for some file. If you have a lot of files that starts from 00 string, Git will be able to find them momentarily just by taking a look at the first two syllables of whatever we want to find and searching for this folder, and so on and so forth. If you have a lot of files in this folder, Git will create another subfolder that will be named C5, right? And so on and so forth. This is a tree structure. And to actually understand what this object is, because we can assume that this is actually a commit. Let's start with this way, and actually it is a commit, but it's hard to say only by looking at a hash that this is actually a commit. And there is a command to get the type of our object, -t, and then you specify the first several characters of our object, and it will return you the type of the object. In this case, this is a commit. Let's try to examine something else. For example, let's go to this folder and do the same operation with this file. Git cat file -t for a b2, and here we have the message that this is actually a tree. And if you examine this file like so, you won't see a lot of information here, because this is also a binary format, so it's not readable. This is why we use a special tool provided by Git, ls-tree, that is able to decode this record and show it to us in readable format. So we type for a b2 as the argument to ls-tree command, and we see our this is actually the initial tree of our repository, as you can remember. And in this case, cat file will contain the single line here. So this is how all the objects are stored, and this is it about an object folder. The next, and actually this is it about this .git folder. It doesn't have any more interesting information for now, right now. So I was talking about that tree can include subfolders, and let's actually try to add subfolders to see how it's viewed in the tree and in the index file. For example, let's create a folder dir1 and create a file, for example file2, and put it into dir1, dir1 and file2.txt, something like that. So now if we take a look at our stage area, or index, also known as index, you see that we don't have this extra file because Git doesn't know about it. And to make it know but not to add it to a stage area, we can actually provide an empty replica of this file just for Git to memorize that we want to keep track of this file. And we do it by command git add, and we specify the flag intend to add. Right? We're saying to Git that we are going to add this file, so please keep track of it for us to be able to use a git diff on it. Now we don't have any changes here because Git cannot compare this newly created file to anything that it knows of. So to give the ability for Git to do it, we need to add this file, and we do it by like so, file2. Its status, if you can see, we don't have this file in a stage area yet, but now if you type git diff, it will show the difference of the file. And now command like git commit -a will work, even though previously it won't work this way, because before we say Git that we have this file, and before Git actually tracked this file. So, and let's take a look at our index file, stage, and here we have a second file, and it has a relative path to it because it's located in the directory, and we have a new blob object that represents this file in the current version. So this is how you add the ability to compare files before you actually commit. Well, comparing a new files before you committed any version of this file to Git repository. And now let's commit our file with a simple git commit -a command. Add file to, and in git log we have an extra commit here. Let's view this commit with cat file. Let's actually first just in case see the type of this commit of this object, and this is indeed a commit. And then let's view, let's decode this record with commit. Here's our commit, here's our tree. And this is here's another way. You can reference tree by the commit that this tree is describing, because as you think about it, every commit has a single tree, because commit saves the state of our repository file structure. So you can reference your tree by referencing a commit. And there is this simple way of referencing the tree, or you can go with actually this way, referencing a tree by commit that this tree this commit owns, or you can go with commit identifier and reference a tree like so. So, and in this case we already have two entries in our list, and the first one being our old file, and as you can see, blob wasn't changed during the latest commit because we haven't changed the first file. And we have an extra entry here, which is a tree of type tree. And it basically means that we have hierarchical structure, and to view whatever listed inside this tree, we need to inspect it. So we take an identifier of this tree, and we use one more git tree command and specify the tree object here. And here we have everything that's stored in this tree. And it means that we only have this one file called file2, and this is a blob, and we can inspect it as we did previously. Blob, which shows us the content of file2. So this is how trees work in case of nested structures. They basically use a reference to another trees, and everything, all that is created during you add changes to index to a stage area before you commit. And exactly when you change it, or when you add it to index, right? When you add it, Git will create a new object in case the file is changed or a new directory is added. And then when you type git commit, Git will take this index and store it to a tree, to a tree that is owned by the latest commit, and that you can view by specifying cat file commit and master, for instance. commit will create this tree, and it will create also a record for a current commit, and it will connect both of these entries, and also it will add a parents and all the other information and store it to database also. So I've mentioned 3 different object types. First one being commit, the most important one. Then commit points to tree, and tree can point to a tree or a blob, meaning a file. And here is the structure how Git keeps track of the versions of each and every one of versions of files that you add and that you work with in your repository. There is another object that I should mention. Is it's called a tag, and we previously already used tags. Let's create some. And there is basically 2 ways you create tag. The simple one is just by providing a tag name and point it to some place. Let's say it's pointing to parents of our head. Now if we inspect log history, we see that this is our tag. And actually if we go to .git directory and speak at refs, here's our tags, and this is basically a file, as we previously saw in head, that includes a commit that this tag is pointing to. So if we inspect what this identifier stands for, file -t, it stands for a commit, right? And this is how a simple tags are stored. And there is another way you can create a tag, and it's called annotated tags. You do it with -a option, and what it is this is the same as tag, only it only stores, well, in addition to referencing a single commit, it also stores the data about the author of the commit, like we have here, and the data when it was created, because by looking at this tag we cannot say where it was created and by whom, and it might be useful sometimes to see this information. So and you create a tag, and actually this tag also should have a message, so you can skip it for now, but you will need to provide it in the editor. And we name our tag, and we point it to some place, like let's point it to the initial commit. And now we need to provide a message, like let's say we create a tag to point it to release of our application. Did I actually create it? Yes, the file is created, the tag is created, and this is similar to this tag in terms of it also is stored in the .git folder, right in refs tags. Here's our tag tool. However, if you inspect it, well, it also stores some identifier, and let's try to see what this identifier stands for with -t, and it stands for a tag, because previously, if you remember, the identifier that is stored in tag 1, it actually references a commit here, but in case of annotated tags we have extra information and connected to our tag, and it means that we need to store this information somewhere, not to store it in a file because it's a bad idea. Maybe Git should store it in a database, in common database. And we can expect annotated tags as if, well, the same way we inspected commits, blobs, and trees. First, as I showed here, you first find out the type of the thing that this tag is pointing to, and then you use a type tag and provide either an identifier of this tag or a name of this tag, doesn't matter. Here's with a name, and let's do it with identifier, the same information. So we have a message here, the data where it was created, the author, and what it points to. It points to object, so it points to this object. Let's inspect what this object stands for. And basically a commit, our first commit, git cut file, commit, add file 1. This is the first commit without a parent. And it also shows here that this commit has a tag. No, actually this describes the name of our tag, that it's called tag2. Anyway, this is the last object type that Git is keeping track of. And as you can see, this structure, this file structure that .git has, .git folder has, is very simple, and most of these files are human readable format, and you can inspect everything in your object database. So here's actually that's, I think, it of what I wanted to share about how Git stores information. And this talk is based on manual Git tutorial part 2, which describes both of these topics. I think that I mentioned everything that this manual includes. I mentioned Git files and objects and different types of objects, how you can view them, and yeah, how index and object trees are connected to each other, and the different ways to inspect the different diff, to use a diff command in different ways, and things like that. You might reference this manual because well, it's useful sometimes to read by yourself here, because it also has a lot of different references to all the other manuals that might be useful to read, like Git Everyday. I guess it will include all the commands that well, the least set of commands that you might use in everyday life, and some glossary and etc. So, but for now, I think that this is it about the topic of object and index, and that's it for this video.